Okay, so let's start with the basics. What exactly are photonic chips?
Okay. So at their core, photonic chips represent a really fundamental change in how we handle information inside a computer. Instead of relying on the movement of tiny particles called electrons through silicon,
Right, the standard way.
they use photons, which are the fundamental particles of light, to transmit and process data. Think of it as swapping out an electrical current for a beam of light within the chip itself.
Okay, light instead of electricity.
Yeah.
And what's the big advantage of using light? Why go to all that trouble instead of just improving the way we use electrons?
Well, the advantages are pretty game-changing, mainly when it comes to speed and efficiency. Light travels incredibly fast, much, much faster than electrons can within a chip.
Way faster.
Plus, it doesn't encounter the same kind of electrical resistance. This means data can be transmitted and processed at speeds we can only dream of with current technology.
The source material had a brilliant way of putting this. It said that electronic chips are like super crowded highways during rush hour. All those electrons bumping into each other, causing delays.
Exactly. Traffic jam.
But photonic chips are like an ultra-fast, friction-free hyperloop, where light just whooshes through without any slowdowns. That really makes it click.
That's a great analogy, yeah.
So lightning fast and more efficient. How do these compare to the chips we're already familiar with, the electronic ones in our phones and laptops, and also these more futuristic quantum chips we hear about?
That's a really important question to set the stage. Looking at the comparison laid out in the material, we can see some key differences in terms of what they use to carry information. Electronic chips use electrons. Quantum chips use something called qubits, which can be a bit mind-bending. They can be 0 and 1 at the same time.
Right, that quantum weirdness.
And photonic chips, as we've discussed, use photons or light particles.
Okay, so fundamentally different ways of representing information. What about how quickly they can process things, speed-wise?
Right. When it comes to speed, traditional electronic chips are certainly fast. We wouldn't call them slow. But photonic chips offer speeds that are in a different league, ultra-high speeds.
Ultra-high. Okay.
Quantum chips, in theory, could achieve exponentially higher speeds for very specific types of calculations, but they are still in the early stages and often require incredibly delicate conditions to operate.
Right, like super cold temperatures and stuff.
Exactly, a very complex setup.
And bandwidth. How much information can these different types of chips handle at once? It's like how many lanes a highway has, right?
Exactly. Good analogy again. Electronic chips have a limited bandwidth compared to both quantum and photonic chips, which offer very, very high bandwidth. For quantum chips, this high bandwidth is crucial for manipulating and communicating quantum information. For photonic chips, it means they can handle massive streams of data simultaneously. Think of downloading a huge movie in the blink of an eye. That's the kind of potential we're talking about.
Wow, okay. Heat generation is something we all experience. Our phones getting warm, laptops getting hot. How do these different chips compare in terms of heat?
This is a major win for photonic chips. Electronic chips generate a significant amount of heat as electrons move through them.
Well,
That resistance,
everyone
right?
can feel it.
Quantum chips need incredibly complex and energy-intensive cooling systems to get them down to near absolute zero just to function.
Which takes a ton of energy in itself.
A huge amount. Photonic chips, on the other hand, produce very little heat.
Wow, that's a massive difference. I can immediately see how that would be beneficial. What about how much energy they use? Energy efficiency.
Well, not surprisingly, this follows a similar pattern. Electronic chips have moderate energy efficiency. Quantum chips, while potentially very efficient in their calculations, require a lot of energy for that extreme cooling we just mentioned.
Right, the overhead.
Photonic chips are highly energy efficient, largely because they don't have the same energy losses from resistance as electronic chips, and they don't need to be kept at those super low temperatures.
That's fascinating. And the last comparison point here is how they're affected by electromagnetic interference, things like radio waves and other electrical signals that can sometimes mess with electronics.
Right. Good point. Electronic chips can be susceptible to electromagnetic interference, EMI, and quantum chips are extremely sensitive to it, needing very careful shielding and isolation to work properly.
So they're delicate.
Very. But photonic chips are immune to electromagnetic interference. Light just isn't affected by it in the same way, which is a huge advantage, especially in environments with lots of electronic noise, like data centers or industrial settings.
So if I'm understanding this correctly, photonic chips really shine when it comes to speed, not getting too hot, using less energy, and being resistant to interference. It sounds like they could overcome some of the fundamental limitations we're hitting with electronic chips.
That's the core idea, yes.
And the best uses listed here, AI, 6G, and even quantum computing really jump out. Why are photonic chips considered so important for these cutting-edge areas?
It all comes down to the ever-increasing demands of these technologies. Think about modern AI models, like the ones powering advanced chatbots or image recognition.
Yeah, they're huge now.
They need to process huge amounts of data incredibly quickly. The GPUs, or graphics processing units that currently do a lot of this heavy lifting, are starting to hit their limits
In what way?
in terms of how much heat they produce, how much power they consume, and their sheer processing capacity. There are physical limits.
Yeah, I've definitely read about the enormous energy footprints of some of these massive AI models. It's kind of staggering.
Exactly. Photonic chips offer a potential way around these bottlenecks. Their ultra-fast speeds and high bandwidth mean they can process those massive data sets needed for training and running AI much faster.
What?
And the fact that they generate less heat and are more energy efficient is crucial for making these powerful AI systems more sustainable and, frankly, more cost-effective to operate.
So faster AI training, more powerful AI.
Yeah.
What about 6G networks? How do photonic chips play a role in the next generation of mobile internet?
Well, 6G is envisioned to deliver dramatically faster data speeds than our current 5G networks, like orders of magnitude faster.
Right.
Photonic chips, with their inherent ability to transmit and process light-based signals at incredibly high speeds, are perfectly suited for the ultra-high bandwidth requirements of future 6G infrastructure.
So they handle the sheer volume of data.
Exactly. They could enable things like truly instantaneous downloads, lag-free holographic communication, and support for a massive number of connected devices, like in the Internet of Things.
That makes perfect sense. We already use fiber optic cables, which transmit data as light for long-distance communication.
We do.
So using light within the chips themselves for processing seems like a logical step to boost speed even further.
It is the next logical step, yeah. Bringing the light processing right down to the chip level.
And you mentioned quantum computing, which still feels very science fiction-y to most of us. How do photonic chips fit into that picture?
Yeah, quantum is definitely out there. It relies on manipulating very fragile quantum states, those qubits we mentioned.
Right.
Photons, being fundamental particles of light, are often used to carry and interact with these quantum states. Photonic chips can offer a more efficient and scalable way to generate, control, and detect individual photons.
Which are essential for quantum computers.
Exactly. They're essential building blocks for many types of quantum computers. Photonic chips could also help in entangling and manipulating those qubits, potentially leading to more stable and powerful quantum computers in the future.
It sounds like photonic chips aren't just a minor upgrade. They could really be a key that unlocks entirely new possibilities in these really important technological frontiers.
That's the hope, yes, a foundational shift.
This leads to another question from the material. Can photonic chips actually help solve some of the real-world headaches we're seeing now, like when AI systems crash or GPUs fail?
That's a really practical and important question to consider because those failures are costly and disruptive.
Definitely.
As we've discussed, today's advanced AI systems rely heavily on GPUs, which draw a lot of power and produce a lot of heat. This heat can lead to systems becoming unstable, their performance dropping off, and even the hardware breaking down,
Yeah.
resulting in those frustrating downtimes.
Definitely not fun when a service you rely on suddenly goes offline. We've all been there.
Exactly. Because photonic chips offer a cooler, faster, and more energy-efficient alternative, they have the potential to significantly reduce these kinds of problems.
That's
Well, less heat generation means less stress on the hardware, which could lead to fewer failures and longer lifespans for these systems. And the higher energy efficiency could contribute to more stable and reliable operation of large-scale AI deployments, like in big data centers.
So it's not just about the theoretical speed improvements, it's also about making these powerful technologies more robust and dependable in the real world. That's a tangible benefit.
Absolutely. Reliability is key.
Now, the material you shared also mentioned Google's Marjana 1 and Willow chips. How do photonic chips stack up against these? I know Google's doing some really interesting work in building specialized hardware for AI.
That's right. Google's Marjana 1 and Willow chips are indeed specialized pieces of hardware, specifically designed to accelerate artificial intelligence tasks. They're called TPUs, tensor processing units.
Okay.
However, it's really important to understand that these chips are still based on traditional electronic designs. They are highly optimized for specific AI workloads like matrix multiplication,
Hmm.
but they still rely on the movement of electrons to perform computations.
Okay, so they're like highly tuned sports cars, but still running on the same fundamental technology as a regular car, using your analogy.
That's a great analogy, yes.
Hmm.
Photonic chips represent a more fundamental shift. It's like moving from gasoline engines to a completely different form of propulsion, like maybe fusion power or something way out there.
Okay, a different paradigm.
Exactly. While Google's chips show impressive progress within the electronic domain, photonic chips have the future potential to outperform them significantly in terms of speed and energy efficiency for a wider range of AI tasks, once the technology matures and becomes more widely available.
Right, there's that caveat.
It's a real paradigm shift in how we think about computation for these kinds of applications.
That gives a really clear sense of where things might be going, but it can't be all upside, right? There must be challenges. What's the biggest hurdle we face in actually adopting photonic chips on a large scale?
You're absolutely right. There are significant challenges. It's not easy.
Yeah.
The biggest one right now is integrating photonic chips into our existing computing infrastructure.
The compatibility problem.
Precisely. Our entire technology ecosystem, from how we manufacture chips in fabs to the fundamental architecture of our computers, motherboards, connections, it's all built around electronic processors.
That makes sense. We're talking about a completely different way of building and operating computer hardware. You can't just slot one in.
Exactly. Moving to photonic computing requires the development of new manufacturing processes, new chip designs that can efficiently manipulate light, tiny lasers, waveguides, detectors on chip,
Complex stuff.
and new ways to connect these light-based chips with other components in a system. How do you get the light in and out efficiently? It also demands significant investment and widespread adoption of these new technologies across the industry. It's not just a simple swap, it requires a substantial rethinking of our current infrastructure.
So it's a bit like trying to build a network of those Hyperloop tubes when all we currently have are roads, a massive undertaking that requires a lot of new infrastructure and coordination.
That's a very apt comparison, as an infrastructure challenge as much as a technological one.
This naturally leads to the question of whether photonic chips will eventually replace electronic chips entirely. It sounds like such a big shift, but will our future devices all be powered by light?
Probably not entirely. The most likely scenario, at least in the near to medium term, is that photonic chips will work alongside and complement electronic chips rather than completely replacing them.
Okay, so a hybrid approach.
Yes. While photonic chips offer compelling advantages for those high-speed, low-power computing tasks, especially in specialized fields like AI, 6G, and quantum computing, electronic chips will likely remain more cost-effective and versatile for general-purpose computing tasks.
So my everyday laptop that I use for browsing the web and writing emails will probably still be running on electrons for the foreseeable future.
Most likely, yes. Electronic chips are a very mature and well-established technology, and they continue to improve. Moore's Law isn't completely dead yet.
Right.
Think of it like this. Electric vehicles are becoming increasingly common, but gasoline-powered cars haven't disappeared entirely and probably won't for a while.
Good point.
Similarly, photonic chips will likely find their niche in high-performance applications where their unique capabilities are most beneficial, while electronic chips continue to handle the vast majority of our computing needs.
That's a really helpful way to visualize it, a collaborative future for these technologies rather than a complete takeover. Well, this has been an incredibly enlightening deep dive. Let's quickly recap the key things we've unpacked.
Absolutely. Let's summarize. We've learned that photonic chips use light photons to transmit and process information. This offers significant advantages in speed, bandwidth, heat generation, and energy efficiency compared to traditional electronic chips,
Key advantages, right?
which makes them a very promising technology for pushing the boundaries of fields like AI training and deployment, enabling the ultra-fast data transmission of future 6G networks, and advancing the capabilities of quantum computers.
We also explored how photonic chips could potentially address some of the practical limitations of current high-performance systems, such as system downtime due to overheating,
The reliability factor.
and how they represent a fundamentally different approach compared to even highly advanced electronic AI accelerators like Google's TPUs.
Right, apples and oranges almost.
While there are considerable hurdles to overcome in terms of infrastructure and adoption,
Hmm.
manufacturing, integration,
Big hurdles, yeah.
the future of computing likely involves a synergistic relationship between photonic and electronic chips, each playing to their strengths in different areas.
Precisely. It's about harnessing the unique capabilities of each technology to push the boundaries of what's possible. Not necessarily replacement, but augmentation.
And considering the potential of photonic chips to revolutionize these cutting-edge fields you're following, it makes you wonder what other seemingly fundamental aspects of our current technology might be ripe for similar paradigm shifts in the coming years.
Mm-hmm. It opens up the thinking.
This transition from electrons to photons in computing might just be the first glimpse into a whole new era of how we process and interact with information. It definitely gives you something to ponder.
It certainly does. The future is bright.
Yeah.
Literally, perhaps.
Indeed. Thanks so much for walking us through this deep dive.
My pleasure. Fascinating topic.